In the last two segments, we talked about the CBC MAC and NMAC to convert a PRF for small messages into a PRF for much larger messages. Those two constructions were sequential in the sense that if you had multiple processors, you couldn't make the construction work any faster. In this segment, we're going to look at a parallel MAC that also converts a small PRF into a large PRF, but does it in a very parallelizable fashion. In particular, we're going to look at a parallel MAC construction called PMAC that uses an underlying PRF to construct a PRF for much larger messages. In particular, the PRF can process much longer messages that can have variable length and have as many as L blocks in them. Now the construction works as follows. We take our message and we break it into blocks, and then we process each block independently of the other. So the first thing we do is we evaluate some function p and we XOR the result into the first message block, and then we apply our function f using a key k1. We do the same for each one of the message blocks, and you notice that we can do it all parallel. All message blocks are processed independently of one another. And we collect all these results into some final XOR, and then we encrypt one more time to get the final tag value. Now for a technical reason, actually on the very last block, we actually don't need to apply the PRFF, but as I said, this is just for a technical reason, and I'm going to ignore that for now. Now I want to explain what the function p is for and what it does. So imagine just for a second that the function p isn't actually there. That is, imagine we actually directly feed each message block into the PRF without applying any other processing to it. Then I claim that the resulting MAC is completely insecure. And the reason is that essentially no order is enforced between the message blocks. In particular, if I swap two message blocks, that doesn't change the value of the final tag. Because the XOR is commutative, the tag will be the same whether we swap the blocks or not. As a result, an attacker can request the tag for a particular message, and then he obtains a tag for a message where two of the blocks are swapped, and that counts as an existential forgery. So what this function p tries to do is essentially enforce order on these blocks. And you notice that the function takes, first of all, it's a keyed function, so it takes a key as input. And second of all, more importantly, it takes the block number as input. In other words, the value of the function is different for each one of the blocks. And that's actually exactly what's preventing this blocks swapping attack. So the function p actually is a very easy to compute function. Essentially, given the key and the message block, all it is just a multiplication in some finite field. So it's a very, very simple function to compute. It adds very little to the running time of PMAC. And yet, it's enough to ensure that the PMAC is actually secure. As we said, the key for PMAC is this pair of keys, one key for the PRF and one key for this masking function p. And finally, I'll tell you that if the message length is not a multiple of the block length, that is, imagine the last block is shorter than full block length, then PMAC actually uses a padding that's similar to CMAC so that there is no need for an additional dummy block ever. So that's the PMAC construction, and as usual we can state its security theorem. So the security theorem, by now you should be used to it. Essentially it says that if you give me an adversary attacking PMAC, I can construct an adversary attacking the underlying PRF plus an additional error term. And so since again the PRF is secure, we know that this term is negligible, and so if we want this term to be negligible, we know that we need this error term to also be negligible. Here, as usual, Q is the number of messages that are MAC'd using a particular key, and L is the maximum length of all those messages. And PMAC is secure as long as this product is less than the square root of the block size. So for AES, this would be 2 to the 128. The square root, therefore, would be 2 to the 64. So the MAC would be secure as long as Q times L is less than 2 to the 64. And every time as it gets closer to that value, of course, you would have to change the key in order to continue macking more messages. So the main thing to remember is that PMAC also gives us a PRF, and when it processes the message blocks independently of one another. Turns out that PMAC also has a very interesting property, namely that PMAC MAC is incremental. So let me explain to you what that means. So suppose the function f that's used to construct PMAC is not just a PRF, but in fact a permutation, a PRP. So we can actually invert it when we need to. Now suppose we've already computed the MAC for a particularly long message m. And now suppose just one message block of this long message changes. So here m1 is changed into m'1, but the remaining message blocks all remain the same. For other MACs like CBC MAC, even though only one message block changed, you would have to recompute the tag on the entire message. Recomputing the tag basically would take time that's proportional to the length of the message. It turns out with PMAC, if we only change one block or a small number of blocks, actually we can recompute the value of the tag for the new message very, very quickly. And let me ask you a puzzle to see if you can figure out how to do that yourself. And remember, the function f is a PRP and therefore is invertible. So let's see if you can figure out how to compute the MAC and the new message by yourself. So it turns out this can be done, and you can quickly recompute the tag and the new message using this third line here. So just to make sure we all see the solution, let's quickly go back to the original diagram for PMAC, and I can show you what I mean. So imagine this one message block changed into some other block, say changed into m'1. Then what we could do is we can take the tag on the original message before the change was made, so we can invert the function f and determine the value before the function f was applied. Now, well, since we now have an XOR of a bunch of blocks, what we can do is we can cancel out the XOR that came from the original message block, basically by XORing this value that came from the original message block into this XORed accumulator, and then XORing again the value that would come from the new message block back into the XOR accumulator, and then apply the function f again. And that would give us the tag for the new message where just one block was changed. So in symbols, basically, I wrote the formula over here. You can see basically we decrypt the tag, and then we XOR with the block that comes from the original message block. We XOR again with the block that comes from the new message block, and then we re-encrypt the final XOR accumulator to get the new tag for the message with the one block changed. So that's kind of a neat property. It kind of shows that if you have very large messages, you can very quickly update the tag. Of course, you will need a secret key to do the update, but you can quickly update the tag if just a small number of message blocks changed. Okay, so that concludes our discussion of PMAC, and now I want to switch topics a little bit and talk about the concept of a one-time MAC, which is basically the analog of the one-time pad, but in the world of integrity. So let me explain what I mean by that. So imagine we want to build a MAC that is only used for integrity of a single message. In other words, every time we compute the integrity of a particular message, we also change the key, so that any particular key is used only for integrity of one message. Then we can define the security game as basically saying the attacker is going to see one message, therefore we only allow him to do one chosen message attack. So he gets to submit one message query, and he is given the tag corresponding to that one message query, and now his goal is to forge a message tag pair. Okay, so you can see his goal is to produce one message tag pair that verifies correctly and is different from the pair that he was actually given. As we'll see, just like the one-time pad and stream ciphers were quite useful, it turns out one-time MACs are also quite useful for the same applications where we only want to use a key to encrypt or to provide integrity for just a single message. So as usual, we would say that a one-time MAC is secure if basically no adversary can win this game. Now the interesting thing is that one-time MACs, just like the one-time pad, can be secure against infinitely powerful adversaries. And not only that, because they're only designed to be secure for one-time use, they can actually be faster than MACs that are based on PRFs. And so I just wanted to give you a quick example of one-time MAC. This is a classic construction for a one-time MAC, and let me show you how it works. The first step is to pick a prime that's slightly larger than our block size. In this case, we're going to use 128-bit blocks, so let's pick the first prime that's bigger than 2 to the 128. This happens to be 2 to the 128 plus 51. And now the key is going to be a pair of random numbers in the range 1 to r prime, so 1 to q. So we choose two random integers in the range 1 to q. Now we're given a message, so we're going to take our message and break it into blocks, where each block is 128 bits. And we're going to regard each number as an integer in the range 0 to 2 to the 128 minus 1. Now the MAC is defined as follows. The first thing we do is we take our message blocks and we kind of construct a polynomial out of them. So if there are L blocks in our message, we're going to construct a polynomial of degree L, and you notice that the constant term of this polynomial is set to 0. And then we define the MAC very simply. Basically what we do is we take the polynomial that corresponds to the message, we evaluate it at the point k, that's one half of our secret key, and then we add the value a, which is the second half of our secret key. And that's it. That's the whole MAC. So just basically construct the polynomial that corresponds to our message, evaluate that polynomial at a half of the secret key, and add the other half of the secret key to the result, and of course reduce the final result modulo q. Okay, so that's it. So that's the whole MAC. It's a one-time secure MAC. And the way we argue that this MAC is one-time secure, essentially is by arguing that if I tell you the value of the MAC for one particular message, that tells you nothing at all about the value of the MAC at another message. And as a result, even though you've seen the value of the MAC on a particular message, you have no way of forging this MAC on some other message. Now, I should emphasize that this is a one-time MAC, but it's not two-time secure. In other words, if you get to see the value of the MAC on two different messages, that actually completely compromises the secret key, and you can actually predict the MAC for a third or fourth message of your choice. So then the MAC becomes forgeable. But for one-time use, it is a perfectly secure MAC, and I'll tell you that in fact this is a very fast MAC to evaluate. So now that we've constructed one-time MACs, it turns out there's actually a general technique that will convert one-time MACs into many-time MACs. And I just wanted to briefly show you how that works. So suppose we have our one-time MAC, let's call it S and V for signing and verification algorithms. And let's just assume that the tags themselves are n-bit strings. In addition, let's also look at a PRF, a secure PRF, that also happens to output n-bit strings, but also takes as inputs n-bit strings. Let's now define a general construction for a MAC. These MACs are called Carter-Wegman MACs, that works as follows. Basically what we would do is we would apply the one-time MAC to the message M, and then we're going to encrypt the result using the PRF. So how do we encrypt the result? Well, we choose a random R, and then we compute kind of a one-time pad from this R by applying the PRF to it, and then we XOR the result with the actual one-time MAC. So the neat thing about this construction is that the fast one-time MAC is applied to the long message, which could be gigabytes long, and the slower PRF is only applied to this nonce R, which is then used to encrypt the final result of the MAC. And you can argue that if the MAC that was given to us as a building block is a one-time secure MAC, and the PRF is secure, then in fact we get a many-time secure MAC that happens to output two n-bit tags. So we're going to see Carter-Wegman MACs later on when we talk about authenticated encryption. And in fact, one of the NIST standard methods for doing encryption with integrity uses a Carter-Wegman MAC for providing integrity. I wanted to mention that this Carter-Wegman MAC is a good example of a randomized MAC where this nonce R is chosen afresh every time the tag is computed. And so if, for example, if you try to compute tag for the same message twice, each time you'll choose a different R, and as a result you'll get different tags both times. And so this is a nice example of a MAC that's actually not a pseudo-random function, not a PRF, because a single message could actually be mapped to many different tags, all of which are valid for that one message. To conclude our discussion of the Carter-Wegman MAC, let me ask you the following question. Here we have the equation for the Carter-Wegman MAC. As usual, you see the nonce R as part of the MAC. And the second part of the MAC I'm going to denote by T. This is basically the one-time MAC applied to the message M, and then encrypted using the pseudo-random function applied to the nonce R. So we'll denote the result of this XOR by T. So my question to you is, given the Carter-Wegman MAC pair R, T for a particular message M, how would you verify that this MAC is valid? And recall that this algorithm V here is the verification algorithm for the underlying one-time MAC. So this is the right answer, and to see why, just observe that this XOR here decrypts the quantity T to its plaintext value, which is basically the original underlying one-time MAC, and so we can directly feed that into the verification algorithm for the one-time MAC. The last type of MAC I wanted to tell you about is one that's very popular in internet protocols. It's called the HMAC. But before we talk about HMAC, we have to talk about hash functions, and in particular collision-resistant hash functions, and we're going to do that in the next module. So this is the end of our first module on MACs, and I wanted to point out that there's really beautiful theory that went into constructing all the MACs that we saw. I kind of gave you the highlights and showed you the main constructions, but there's really quite a bit of theory that goes into constructing these MACs, and if you'd like to learn more about that, I kind of listed a couple of key papers that you might want to look at. Let me quickly tell you what they are. The first one is what's called the 3-key construction, which is the basis of CMAC, a very elegant paper that gives a very efficient construction out of CBCMAC. The second paper is a more technical paper, but basically shows how to prove the bounds of CBCMAC as a PRF. The third paper talks about PMAC and its construction, again, a very cute paper. The fourth paper talks about security of NMAC and HMAC as well. HMAC we're going to cover in the next module. The last paper I listed asks an intriguing question. Recall that all of our constructions, we always assumed that AES is a pseudo-random function for 16-byte messages, and then we built a pseudo-random function and therefore a MAC for much longer messages. This paper says, well, what do we do if AES is not a pseudo-random function, but still satisfies some weaker security property called an unpredictable function? And then they ask, if AES is only an unpredictable function, but not a pseudorandom function, can we still build MACs for long messages? And so they succeed in actually giving constructions just based on the weaker assumption that AES is an unpredictable function, but their constructions are far less efficient than CBCMAC or NMAC or PMAC that we discussed in these segments. And so if you're interested in a different perspective on how to build MACs from block ciphers like AES, please take a look at this paper, and there are actually some nice open questions to work on in this area. So this concludes our first segment on integrity, and in the next segment we're going to talk about collision resistance.